Give me a second to do a small switch. Okay, right. Thank you. So let's start. uh, so the last class, that was yesterday, we were talking about binary search trees. Actually, we started from binary trees, and then we looked at what we realized in binary trees is that we have trees which are uh, easier to visualize, build when it is binary, because each node has a maximum of 2 children. But then we also have a problem in a regular binary tree. So the problem is that if you want to do search, if you want to order them and so on, it's not possible in a regular binary tree. So then we discussed about a specific type of binary tree known as, or what we call the binary search tree, right? So a binary search tree is OBST in short, right? So is a binary tree that we can use to search, right? So how do we search is by putting the elements in the tree or the nodes in the tree in an order. So the order is very simple. If you take any node, the elements that are smaller than particular node will be on the left subtree, and elements that are larger will be on the right subtree, right? So if you take a node, everything, here can be a tree here, there can be a tree here. So everything on the left side are smaller, everything on the right side are larger. So that's how we build a binary search tree. So we have to maintain this property while we are building the tree, or while we are adding nodes or items to the tree. And also the same applies when we are even removing items, which makes the life of search, the intention of this tree is searching, easier. But at the same time, we also realized such searching might not be always good, because the way how we build a binary search tree depends on not just the value that is in the tree, or the nodes, the value of the nodes in the tree. The tree doesn't depend, or the tree structure doesn't depend only on the values, but also in the order in which we add the values. Like for example, if I'm making a tree using numbers 1, 2, 3, 4, 5, the same set of values, if I make a tree using 2, 3, 1, 5, 4, these are going to be two different binary search trees, although they both have the same elements. They are not going to be the same binary search tree, which means the binary search tree is unpredictable. Unpredictable in the sense it depends on the order in which we put the item. Which also means in certain situations, for example, if we have an ordered list inserted to a binary search tree, what we end up is in a tree that is skewed, very much skewed, and will be more like a list, not a tree anymore. So that's not a good idea. So then we thought, okay, what do we do about it is to build trees that can balance its height to maintain some perfect binary tree behavior. And one such balanced tree is what we are going to discuss today. The balanced tree we are going to discuss today is called AVL tree. So AVL is actually name of two people. I'll come to that little while later. And this is the first binary search tree that was proposed in the literature. The first one, because binary search tree, balanced binary search tree, that is proposed, because without the balancing factor, the binary search tree becomes almost useless, right? Why? Because it can have unpredicted behavior. It can be bad in situations where the order in which we put items are bad. So those are the reasons why we decided a balanced tree is a requirement. And in somewhere about 1960s, two mathematicians or computer scientists proposed the idea of an AVL tree, or basically a balanced tree, and they named it uh, um, after them. And that is what we are going to discuss today. And AVL tree is very popular. There are, okay, so AVL tree is very popular and used in lot of practical application. So today we'll see how AVL tree works and how we can build one, how we can identify AVL trees, all sort of different aspects of an AVL tree. Right, so let's go there. Actually, before I go there, I also wanted to remind you, in the very first class, I also told you there is this website built by a university on for learning data structures. Very useful website. It's called visualgo.net. I strongly propose you to look at it and see how some explanation. They also have visualization. They also have quizzes. So it's good for you to try a website like this. So in fact, I'm on the BST, or the binary search tree part of the website, but the website has a lot of other things. I'll just go back. So it's built by the National University of Singapore, their computing school. And they also have things in the arrays and like just algorithms like sorting and so on, linked list and whatnot. And the one we are focusing now on is the binary search tree. So if you go to binary search tree, in fact, they have a lot of items related to binary search tree, starting from the usual binary search tree, and like AVL tree, balanced binary search tree. They are taking AVL tree as an example, and those are the differences, and also then all what I discuss and some quizzes. How you when you insert, but how it works, when you remove, how it works, how you can search. They are nicely presented, even removing one of the challenging parts I mentioned to you earlier in the last class. And then more details on the balanced binary search tree, which is the AVL tree, and even quizzes. As you can see, there are quizzes everywhere that you can try out and verify whether you had done right and you understood right. In fact, the AVL tree also is proved to be the best balanced tree possible. Actually, algorithm wise, there are a number of different, or the idea wise, there are a number of balanced binary trees proposed. We'll look at some of them in the next classes as well. But AVL tree is supposed to be the best in terms of balancing, the balanced tree that we can make. We'll learn about that today. So then when it comes to AVL tree, how do we mathematically prove how balanced an AVL tree is? And those proofs and details are mentioned here. In fact, like I will not go into the proof in my discussion, but it's an interesting idea for you if you are those who are mathematically inclined, can look at how we can prove how good, efficient an AVL tree could be. Yeah, so that's the best out there. So if you can come up with something better, I think it's some work that you can actually publish, right? So there are a few other trees, balance trees, where the balance factor is a bit relaxed. AVL tree has the most stringent balance factor, the constraint balance factor. How balanced a tree can be. I hope, but you understand what you mean by balancing. Balancing is to make sure we go towards the perfect tree as much as possible, which means we are reducing the height or the number of levels on a tree as much as possible. The lower the height or the balance of a height or the levels of a tree, the better balanced it is, right? So that's the idea. Uh, so those details are here. I should suggest you spend some time, go through this website, because it goes into example. Like for example, if you go here, that is a particular binary search tree. I mean, you can just make one, and you can even create a binary search tree with some random numbers or a skewed one. let's say a left skewed one, you can see that, a right skewed one, and then you can like search in a tree like that. What happens if I want to search for a number like 53? Um, right, so an algorithm for searching, it works and it identifies how it shows in simulation how the search works going through the algorithm. Not just search, it also has other, as you can see, insert, remove, finding the predecessors, successors, and traversing, meaning going through all the element in a tree. So we discuss about these different type of traversal in order, pre-order, post-order. Those, like, let's just take an example, create a random one. It's, let's say, 15 elements, a tree like that. And if you want to traverse this in order, you can see how the traversal works. And it shows not only the simulation, but also how it goes through a, what do you call, a pseudocode, right? So that's an in-order traversal. So you can in fact learn how this works and visualize. So that's the most important and challenging part to do. But when you do it once, it becomes easier. This is just the binary search tree. Binary search tree is an easier one actually, because it is just simple, right? So you just have to do left, right when you are searching. If it is in order, left, root, right. So it's simple and you just have to recursively follow that pattern. But when it comes to more complex like AVL, a balance tree, there are a few other complexities. We will be discussing those today. How do we make sure the balance is maintained, right? So those are things that we'll be discussing today, and the simulation will really help in situations like that. So I suggest you spend your own time, because I will not be like using the simulation to do every step and show. So but spend your time, go through this website, and particularly now we are discussing about BST, and therefore the BST binary search tree part of it. I strongly recommend you all try this out. Let me go back to the slide deck. And with that background, we are going to get into the binary search, particularly the balanced binary search tree. Although I call it balanced trees, it's actually a balanced binary search tree. The binary search tree we are talking about is AVL, right? So I in fact like already mentioned a few things here, but just to put them in text. And by the way, I also am uploading all this material to the to fields, so you should be able to access them all. Yesterday there were some questions, so I also have. I'll just go back and show that as well. So we are complete. So these are things I already have uploaded. The slides for the first lecture, PDF of it. That's the physical lecture we had. This is the slides for the second lecture, the PDF of it, and also the video recording of the second lecture. This is today's one, and the PDF. I'll also upload the recording that's happening now. So you get access to all this material, and I strongly recommend you to look at this website, visualgrow.net, where you have very interesting, simple explanation, simple quizzes. This will really be useful when you are going to go to the lab, because in the lab we are going to write code, and the understanding of the algorithm, the steps you have to follow, is very important when you are writing the code. Okay, let me go back. So today, like I mentioned, the focus is we already know like why the binary search tree, the usual, the plain binary search tree I call it, but it's a binary search tree. Why it fails. I have shown enough example even yesterday how this degradation happen or the linearity comes into play. And And therefore, having some sort of balancing is very important. Without balancing, it's really bad. I'll show you some numbers, how bad it is. And you can also imagine, right? So if you have like 10 nodes, and if you are going to have balance like a skewed tree, you'll have to go through 10 elements to find something if you are searching, for example. So the complexity of searching is in very much like an array or actually and like yeah. So but even an unsorted array, right? So not sorted array, we can also try some other algorithm to find something faster. So that's how bad it is when it comes to unbalanced trees. Even binary search tree could be really unbalanced, depends on the order in which we insert items. So there is a need for balancing. So AVL trees is what you're going to learn today. They are considered self-balancing trees. Um, and what do you mean by self-balancing is that whenever a change happen to the tree, the construction of the tree is such that it will automatically balance. When I say a change happen to a tree, there are only two occasions where the change happens to a tree. One, we are adding a new item or a new node to the tree. The other is we are removing one. So when you are adding a new item or when you are removing an item from the tree can become unbalanced. So then we follow a process which is part of the tree's structure through which we'll be balancing the tree back. That's the idea, and that balancing happens as part of the tree data structure, right? So it's part of the program. So when you're inserting an item, you don't just insert an item like in a in a binary search tree. In a binary search tree, you'll be just inserting an item following the procedure we discussed in yesterday's class. But in a balanced binary search tree, like the AVL tree, when you insert, you don't just insert, you'll also check for the balance after inserting. If the balance factor is violated, you will have to balance it. So balancing is happening there as part of the insertion. Same applies for deletion. When you're deleting, and if there's some change in the balance, otherwise the balance is violated, the balancing function or the balancing procedure has to be called to balance the tree back. AVL tree has 4 ways to balance any situation. When an imbalance happens, there are 4 ways to balance it, and they are done by what we know as rotations. I'll explain them clearly as we go. We do something called rotation, tree rotation to balance, and there are 4 situations through which a tree can become imbalanced. 4 situations. In short, they are referred to as LL, left, left, right, right, left, right, right, left. I'll explain them as we go. So we'll look at the 4 different situations. These are the only 4 situations that an AVL tree can become not balanced. And it's possible for us to balance it back using 4 techniques for each different type of, these are 4 different ways in which the imbalance can happen. And then there are 4 techniques we can use, one for each, to balance them back. We'll discuss them. That's the main item for today's class. And then we'll also understand the complexity. We already know, right? So binary tree, if we have a perfect binary tree, then the search complexity is very good, which is going to be log based to the number of nodes, right? So that's the usual situation. When basically the idea is every time we add nodes, they are going to be divided into 2, right, binaries, right? So here we have a tree with 7 nodes, but in 3 levels, right? So the next we can add 2 more, 2 more, 2 more, 2 more, and so on. So each level we get 2 times the number of nodes in the previous level. And if you have a perfect tree like this, then the search becomes, so although now we have 1, 3, 7, and 8, 15 nodes, we just had to go through them only 1, 2, 4 times, right? So once here, once here, once here, once here. and then we are done with the search. So it's the search complexity is log 2n, but it's not always true. And we know this same tree can also be a worst binary search tree where all these 15 items can be just on one side or the other, which is the worst pair. So this is why we are talking about a balanced tree, and we are talking about the AVL tree as the balanced tree here. So therefore, complexity of there is now for we also already had discussed the complexity of search, complexity of adding things to a binary search tree, which is easier. Deleting sometimes become little complicated. We discussed it yesterday. Of a binary search is not so complicated, little, and those are the little complication, but in general binary search tree complexity is very good. But when it comes to searching, finding, depends. If it's a perfect binary search tree, then it's really good, or like a balanced binary search tree is really good, otherwise it's bad. So we are going to discuss today how we can balance, and also we are going to discuss how we can uh, how it reduces the complexity, the search complexity. At the same time, it also adds something to the balancing complexity. So now we have to add balancing to our algorithm, which makes it little more, the algorithm becomes a little more complex, but searching becomes so easy. It becomes almost close to a perfect balance, perfect binary search. We'll also look at some examples today. Give me a second. Here. Right, so let's proceed. So that's the plan for the rest of today. We'll be looking at some examples as well. So like I have already mentioned, the point is unless we control the height of a binary search tree through some mechanism, here we are talking about a mechanism called self-balancing. Right, so self-balancing means it's not part of the data structure, but the data structure when we are making changes, we will have an algorithm that will make that balancing fact or balancing act actually, right? So it will change, do some work to make sure the tree is balanced or the binary search tree here is balanced. Right? That is, what do you mean by balancing is to reduce the height or the levels of the tree as small as possible, right? So very much closer to a perfect tree. That's what we are trying to do here. And I think I already have discussed, and also I have shown this example last time. So I just have included it here for your like later references because I'm sharing the PDF with you or the slides with you. So you know this has happened, and I have already shown examples. And what it means is that when this sort of situation happens, is a worst case where the order is it's an ascending order. Same applies for descending order. Then the search operation becomes worse than something like even a linked, an ordered array or a list. Because an order array or a list, we might be using a different algorithm for searching, like a fast algorithm like binary search or any other searching algorithm which are faster. But here it's not we don't do that. So because we rely, the searching algorithm here relies on the data structure, right? So searching is very simple, but the data structure makes sure the search is faster. Binary search or binary in a binary search tree, the search is a simple idea of just traversing through the tree itself, right? So compared to a linked list or an array where the data structure is linear, but we can do a, if you have an ordered array or a linked list, we can do a binary search, which is faster. There, the algorithm itself becoming more complex and traverses through the tree, or sorry, traverses through the array or the list in a different order, right? So that we don't do that here. So that it becomes bad and worse than an array, an ordered array. That's where we are uh, right now. And we also have discussed why it happens even earlier. So order dependency, I mentioned about it. It's not just about the elements, but also the order in which we put the elements is how the tree is going to be made. Particularly when you have inputs which are sorted, we have a serious problem. And there's no way of automatically getting it corrected in a regular binary search tree. Right? So these are things I already have discussed. Right. So, but then putting them in the slides. This here is an example, right? So if we have like smaller trees, like 10 elements, then the number of levels could be like either 3 or 10, right? So that's the difference. Looks like a small difference, but if you think of a really large tree, like 1 million elements, then if you do like a skewed, completely skewed tree, then you'll have to do a comparison of 1 million elements to find search and find something. But if you have a perfect tree, then it's just 10 to the power 20 is more than, oh, sorry, 2 to the power 20 is more than 1 million, right? So it's just 20 different comparisons you'll have to do if you have a perfect tree. So you can see how much different it is. Instead of searching 1 million, we just have to search 20. If you have a perfect tree, obviously a balanced tree. If you don't have a balanced tree, it could be anything between 20 to 1 million. The worst case, it could be 1 million. So you can see there's a big difference in terms of how long a search could take. So because of that, we'll have to spend time doing balancing, right? So that's the reason why balancing is very important here, right? So if we have a balanced tree, so here is a tree which is sort of balanced, not perfectly obviously, but it's better than the one we are showing you earlier, like completely skewed, right? So a balanced tree, the idea is the subtrees have similar heights. Right, so this is the idea of how balancing work, but I'll explain explicitly how AVL tree is done. And it, like I mentioned at the beginning, AVL tree is one of the most possible or the one with the highest constraint, meaning the most balanced possible tree available so far. Uh, I mean, if you are given a chance to take all the values and all say all the data, like let's say you have 1 million data, and if I ask you, okay, these are the 1 million numbers, make a tree that is balanced. It is possible for you to go through this data and come up with the perfectly balanced tree. It's possible. It's obviously possible. But the point is not that, right? So the point is this data is coming, the data points are coming one after the other. They are getting inserted. We'll have to build a tree such that it's balanced, right? So that's the difficult part. So in a binary search tree, it could be like, if you are lucky, it could be good. If you are not, it could be like completely bad, like really bad, right? So or it could be anything in between, right? So when you are making a tree, the challenge is not that I know all the elements and then reorder the elements so that and start inserting so that it becomes a balanced tree. That's easy to do, but that's not a practical thing, right? Because wherever the tree structure is used, it's a dynamic structure. The data are going to come in and go out as and when they appear. Not like we have access to all the data and we just want to make a tree, right? So therefore, balancing is the act that makes the tree as perfect as possible. So for now, the best possible balancing algorithm that is out there is AVL. You can come up with anything better, right? So, but obviously that algorithm has to be something that takes in data one after the other and then does balancing as we go, as we are building the tree. Same applies for deleting. So if you are deleting an element, again, we'll have to go through the same process. An element is gone. When an element is gone, what happened to the tree? And then you can balance it back, right? So that is the best algorithm is AVL. So AVL is not going to make, why I am explaining this to you is to tell you AVL tree is not going to make a perfect balanced tree. You might wonder, okay, I have these 10 elements. AVL tree is not giving me the best possible perfect tree. Yes, it won't. Why not? Is because this AVL algorithm is such that we sees one element at a time. And using those elements, it's try to balance as much as possible. It will not be knowing all the elements in advance. If it knows, it could be better. But we don't have like a situation like that, and therefore there is no such algorithm, and it doesn't make sense. So because it's also true for deleting, right? So in a deleting, if I delete an item, then I'll have to go through all the element to come rebuild the tree. So that's not possible. Only possibility is to balance it using an algorithm, and therefore the balancing will not make a perfectly balanced tree. Luckily, we might come into a luck and it's possible, but mathematically it's not possible to make such tree all the time. So it's going to be balanced, not perfect. So these are things we will guarantee in a binary like a AVL tree or a balanced tree. But then these are problems in a regular binary search tree, right? Binary search tree can be fast, but performance depends entirely on the input pattern, right? So, but the goal what we have is to make a binary search tree that has a predictable order log to n complexity, right? So log to n is what we want because that is very much what a balanced binary search tree is. But we could end up worse, and it's just could be big O n. We don't want that. So how do we? And also the goal, as you can see here, is not for just one specific situation which could occur in a binary search tree, but here for all possible inputs, right? So any order we put input, we should have a predictable order log n complexity, right? So log n complexity is for any order possible, right? So independent of the order in which we put numbers, it will be balanced such that we will come closer to log n, right? So that's the idea. So that's the idea of making this tree, the AVL tree. Like I said, AVL tree is named after some now Russian people. It was those days Soviet Union. And so the A in AVL for Adelson, and then we also have Adelson Belsky is one person, and the other one is Landis. So AVL is AV for one person's name, L is for the other one. So that's how it's named. Maybe one contributed more, another one less. I haven't read the history of this, so I don't really know. But that's the idea behind. It's just a name of people, and that's how it's named. And the main part is this is the best possible binary search, balanced binary search tree. Balance meaning self-balancing. I'll show how, right? The idea is to reduce the height, and there are other binary search balanced binary search trees. Example: red black tree, splay tree, and B tree. These are we'll also look at one or two. Actually, we'll look at red black tree and B trees in the next class to see how they are different. In fact, like they are a bit more relaxed or less constrained than AVL tree. AVL tree is the first one to get introduced, and the most balanced possible algorithm so far, like I told you. So what's AVL tree? Here's the mathematical definition for an AVL tree, or a formal definition for an AVL tree. This is how they had defined it. So an AVL tree is, first thing, it's a binary search tree. So meaning it has to satisfy the binary search tree properties. We already have discussed and defined what binary search tree properties are. So it has to be binary search tree. So whatever we do, any rotation, any like balancing act we do, it has to still satisfy the binary search tree property. It's simple, right? The binary search tree property is that every node should have a maximum of two children, 0, 1, or 2. That's the first thing, binary search tree, so that every node, the left subtree will be having elements that are smaller than that particular node. Right subtree will have elements that are larger than that particular node, which applies to every node in the tree. That's what a binary search tree is. Now we are adding more to the binary search tree definition to make it AVL. The additional thing we are adding is about this balance factor. There's only one thing we are adding, and that is this balance factor, right? So we are saying a binary search tree with balance factor -1, 0, or +1 is an AVL tree. So the balance factor can be either 0 or plus or -1, right? So when you say balance factor, the balance factor we are talking about every node, not on a specific node, not just on the root. Every node. In fact, like if you remember, even the binary search tree definition is also every node, not just for the root, right? So it's for every node. Yeah, it's for every node. So every node had to satisfy the balance factor. Obviously, it has to satisfy the binary search tree properties like two children maximum, left subtree the element should be smaller than the root, and then that particular node, and right subtree element would be larger than the node. Those are things that are coming from the BST. And here is one more thing. So what is this balance factor? It is defined. Oops. Give me a second. I click something. Yeah. So the balance factor is defined using height, right? Two heights. So basically the balance factor is the height of the left subtree minus the height of the right subtree. So if we have a tree, left subtree, right subtree, and if both of these heights are equal, then the balance factor of this node is going to be 0, right? If the height of the left subtree is higher, more, and this is less, this is, let's say, left subtree L, right subtree R. If L minus R is greater than 1, then it is not balanced, right? So this one, if it is 1, then fine, right? If it is 1, then it is still balanced. If it is 0, still balanced, both are equal. If it is 1, the difference is 1, it's still balanced. If it is -1, which means R is larger, one height larger, that's also okay. So you can see we are not like restricting it too much as well. We are not saying the balance has to be 0. If we say the balance has to be 0, then it is going to be perfectly balanced, but it's difficult to make. So the AVL tree is defined by saying the balance factor can be any number between -1 and +1, which means it can this side can be one more, or this side can be one more, or both can be equal, right? So that's how the balance tree is defined, and the AVL tree is defined. That's the definition. We'll see how it looks in practice, right? So one more thing, how do we the AVL tree algorithm defines height uh, in a little different way, like it's specific, but then it's sort of not so important, because it, as long as the definition is consistent across your calculations, it's okay. I hope, I mean, I'll explain it further as I go. So here is the definition for height of a node. So as you can see, the height of the node is the length of the longest path from the node to a leaf, right? So the longest path, like if you have a node, and if you have obviously binary search tree, and therefore there's only two subtrees, right? And there could be a path. So there is the lowest level of leaf, the lowest level of leaf here, and from here, how many steps you had to come to this node. From this side, how many steps you had to come to this node, and if so, the height of this node is going to be decided by looking at which one of these two is the longest, right? If this is a shorter one, then we'll take this to decide the height of that, right? So that's how the height is calculated. It's very intuitive. I think we already have discussed it earlier as well. But there are special cases mentioned. If we have a leaf node, right? So a node without any children, and that node's height is it's defined as 0. As you can see, leaf node's height is defined as 0, right? So height of this node without any children is 0. And if we have if you're talking about the height of uh, uh, a subtree with null, meaning there's nothing. Like, let's say, so there are two subtrees possible here, right? One possible here, one possible here. There could be a subtree here, there could be a subtree here, but those two don't exist. When they don't exist, the height of those are defined as -1. Because mathematically, if you want to prove something, we'll have to include all those boundary conditions, right? So the height of null trees, which means there's no node, is -1. And height of a node with one child, right? So let's say there's one here. The height of this node, and there's no child there, right? So I'll erase that part. Right, so the height of this tree is going to be so the height of this node is going to be the height of the child plus 1. So the height of the child here is, this is a leaf, and therefore the height of this is 0. And therefore the height of this is going to be height of this, which is 0 plus the 1. It's just mathematically saying like where this is the height, right? So basically the height of this is 1 and height of this is 0. Right? So if we have one child, it's going to be 1. So if we have a multiple child, then you'll have to calculate the height of that particular child. Like, so for example, if you are having one here, this node's height will be the height of this child, which is 1 plus 1. So it's 2, right? So that's just the mathematical way of putting things out. But it's a simple number of the path, right? So the path and the longest path. That's how the height is calculated. This is useful because we are going to write an algorithm, write a program, and also going to maintain. Now, I hope you realize we also had to maintain either the balance factor or the height at various locations, so that we can use it when you want to decide whether a tree is still balanced or it has gone imbalanced. Right? So to decide that, we need to maintain additional data now. A binary search tree doesn't maintain this data. A binary search tree only maintains the right node, left node, and then the value itself. Now we also had to maintain either balance factor or the height so that you can calculate the balance factor. So that's already an overhead, as you would have noticed in terms of storage. So here is an example to explain what I said. I think it's sort of straightforward. I already have explained one. So I'll skip this and go forward, but it is there so that just in case if you want to go back and refresh, this example is here. So when is the node non-unbalanced, right? So if the row node is unbalanced, when is it, right? So that is the question I already answered. So basically, if you have balance factor, which is the balance factor, which is greater than 1 or less than 1, less than minus 1, right? So if the balance factor is going to be anything greater than 1 plus 1 or less than minus 1, then we have an unbalanced node, right? So remember I told you about balancing on each particular node. And little later I'll also show that when you are balancing, you don't really have to balance everywhere. As long as you balance on a particular node, the rest will automatically get balanced. That's how an AVL tree works. When let's say you have a balanced AVL tree or an AVL tree which is obviously balanced, and then you add a node. When you add a node, if an imbalance happens somewhere, so now a node is unbalanced. So then if the node is unbalanced, you just have to balance that node and not worry about anything else, which basically means by property, if one node becomes unbalanced, balancing that node will balance the whole tree. It's proven actually. So those are good things because we don't have to worry about looking at balancing multiple nodes when you do a single change to the tree. A single change to the tree will only make one node. Uh, Sometimes it will not make anything imbalance, by the way, right? So adding a node doesn't always make the tree go unbalanced or any node going unbalanced, right? So adding a node doesn't always make the tree unbalanced. But if adding a node makes the tree unbalanced, by balancing one node, you can basically balance the tree, right? So that's proven. I'll show you examples, right? Just for you to understand or for you to remember. You don't have to worry about balancing and checking every other node to see whether they all. Obviously, we'll have to check every node to see whether a node is unbalanced. Obviously, there'll be only one, and when you do it, you are done. So here are examples, right? So this is obvious. This is some things that we already have seen. And these are both of these trees are unbalanced because they have unbalanced nodes, right? So which nodes are unbalanced here? Right? If you take this is a leaf node and the balance factor is 0 and there's nothing to unbalance here, right? So I mean it's a balanced node. If you take this, right, so this one is 0, this one is -1, and therefore this one is 0 minus 1, so it's 1, right? So the balance factor is 1, and if you take this node, this side we have 2 and the other side we have 0. So 0 minus 2 is 2 or plus 2. So this node, the node that is going to be in red color is the one that is unbalanced node. I don't have to again explain the same for the other side, I hope, and the unbalanced node is this. The difference is that here the balance factor is plus 2, here the balance factor is minus 2, right? So the balance factors are different. Otherwise, both of these are unbalanced trees. And they are unbalanced only because the node that is in red is unbalanced. Only that node is unbalanced and therefore the tree is unbalanced. Other nodes are balanced, right? So that's the balance factor of the other nodes are within the limit, right? Within the limit we have mentioned here, right? So that's where we are. And let's see, go forward and see how we can do balancing and so on. Are there any questions? I keep going. In the example given there, it says that left height of 25 is 1, shouldn't it be 2? Left height of 25 is 1. Maybe was it from this or earlier? Maybe from a previous one. I missed, sorry. Let me look at 25. So when you have the height is defined, leaf node is 0, 1 with 1 children. So this is the height of this is going to be 1, right? So leaf node is 0, this is 1. Yeah, this should be 2. There's some mistake here. You are right. Somebody pointed that out. Yeah, I'll update those. There's some mistake here. So the height of this is obviously 2. Left height. The height of 15 is 1. I think that is what we are talking about here. We are talking about not the height of node 25, but the height of the left subtree and the right subtree, right? So this is the height of the left subtree and the right subtree. I hope you got it. So the numbers are correct, right? So left subtree is the height of this side and the height of this side, right? So if you take 15, then the left one has the left. So we are not talking about the height of that particular node, right? So we are talking about the left height, meaning the left subtree's height and the right subtree's heights. Those are the one which are mentioned here. Why we are mentioning those is because for obvious reason, the definition goes like this, right? If you want to find the balance factor, we had to find the balance factor of the height of the left subtree and the height of the right subtree, right? So here we are talking, just to clarify, those who had doubts, double check, right? So node 25, we are talking about, so when you say left height, we are talking about the height of this subtree, right? And then the height of this subtree, right? So height of this subtree is the height of this. Height of this is 0, height of this is 1, right? So again, height of this is, these individual are 0 and height of this is 1, right? So if you take a node like, because that is what we want, right? So if you want to find the balance factor of 25, is going to be the height of the subtree starting with 15 minus height of the subtree with the root 40, right? So we are talking about the height of these two here, because that is what how the definition goes. If you want to find the balance factor of a node, we are not looking at the height of that node. In fact, like technically, when you think why it is defined like this is because when you want to run through an algorithm, this is how it can be done, right? So if you want to update the balance factor, find the balance factor of this, we'll be looking at the height of the two subtrees, right? So the same applies for 15, right? So 15, if you want to find the balance factor of 15, you will find the height of the left subtree, and which is just the leaf, so it's 1. A right subtree where there's nothing, so it's -1, right? So sorry, leaf is 0. I don't know what I'm talking about. So leaf is 0. Remember the special case, leaf is 0, which I explained here. Leaf node height is 0, right? So it should be 0 for leaf, and this side there's nothing, so it's -1. If you take 40, both sides are leaves, so both sides are 0. And so if you want to find the balance factor of 40, it's going to be the left subtree's height minus the right subtree's height, which is 45, right? So the height of the left subtree, height of the right subtree. So height of the left subtree 30, 30 is the leaf, which is 0. The other one is right subtree 45, it's again a leaf, so 0. So the balance factor is going to be 0. So the balance factor of Node 40 is 0, the balance. So let me just now, I have explained this. Let me just to make sure everybody understand the balance factor of this is going to be 0. This is 0. This is 0. This is 0. This is going to be 1. And this is going to be the difference between the two, the height of this side and the height of this side. And that is going to be again 0. So that's how the balance factors are going to be calculated. Right, so the height balance factors are calculated by looking at the height of the subtrees, not the height of that particular node. That seems to be the confusion someone had. 15, do you want me to explain again? So for somebody is asking me to explain the node 15 again. So if you take node 15, so 15, when you are going to find the balance factor of 15, right? So 15 has 1 here, a null here. Nothing means null, right? So if you want to find the balance factor of 15, we'll have to find the height of left subtree, which is a leaf node. Leaf node's height is going to be 0 minus, and there is null, nothing there, and nothing's height is minus 1, right? So that was already mentioned in the previous slide. So minus 1. That's the balance factor of 15. So the balance factor of 15 is going to be 0 minus minus 1, which is 1. I hope you got it. Right, so make sure, so I mean, it's sort of intuitive and obvious. We can see like the balance factors, how it is, but we are carefully following the definition for good reasons, because the algorithm will become easier, right? So now when you know the height of the subtree, I just have to take that to find the balance factor of a particular node, which which is the parent of those two subtrees. That's how the algorithm works, and it becomes easier to run through the algorithm. That's why it's defined like this. Okay. So yeah, with this, and the balance factors here are going to be positive 2 and negative 2 for the reason I already have explained, right? So yeah, so with that, let's move on further. And here is, I'm not going to prove this. Mathematically, it's possible to prove. In fact, like it is proven by the AVL team actually. The AVL tree, it maintains actually a height of 1.44 times log 2n, right? So it's not log 2n. Log base 2n is the perfect one what we can have, which means 1 times log 2n. But the height maintained by this balancing, where we are giving some room for some flexibility, right? Not a lot of flexibility, some flexibility, where we can have -1, +1, and so on. So the balancing, the height is actually 1.44. So it's not 1, it's above 1. It's almost about 1.5 times, right? So which is not too bad if you think about it, because remember, if you have 1 million nodes, what he said was, usually if we have like a worst binary tree, we'll have to go through 1 million. The best binary tree, we can do it in 2 to the power 10 or something, 2 to the power 20, right? So yeah, 2 to the power 20. So we can do it in 20. 1 million to 20 is the difference, right? So 2 to the power 20. So basically it's 20 is the depth, right? But now with this, even if it is 1.5 times, we'll just go to 30, right? So we'll, instead of doing 1 million, a balanced binary search tree like the AVL tree will guarantee us a height of less than 30, right? So 1.5 times 30 is 1.44. So it's less than 30. So less than 30 is way better than unpredictable 1 million. 20 is good, but 30 is not so bad. Not bad anywhere close to 1 billion, 1 million. So that's what we are working on. I'm not going to prove this. Like I told you, if those who are mathematically inclined, you can go and look at the definition and the proof, all that are available under the AVL tree. Actually, there's a paper, and also a lot of post work done and proof and all that. So that's the the search, the height, with the height comes the search, right? So the search complexity is good. And in the big O notation, this is a constant. So we can say that in big O notation, it's still the same, right? So big O notation. So that's the whole idea, right? The big O notation, 20 and 30 are not so different. They are the same in the big O notation. I hope you learned those things in your algorithms part one complexities, right? So search complexity and therefore log n. Insert has the same complexity because first to insert you had to search. You search, find the location to insert. We already seen how insertion works. Delete again, you do the same, search, find, place, and delete. Insert. Right, I'm back. So we were talking about how the complexity of the AVL algorithm works in different situations. We already know the height is going to be 1.44 times or 1.5 times, which basically means it's not too bad. And in terms of big O notation, the search complexity, insertion, deletion, all of them are going to be in the same order because all of them have have the search complexity basically, right? Because if we are going to an insert, we are going to find, and finding is searching, we have to insert, deleting again finding, but deleting has a little more issue like which was mentioned here, the rotation. Even insertion now has something called rotation. So compared to the like a regular binary search tree, there's some additional thing we are going to do for both insertion and deletion, like I told you. So when you are doing insertion or deletion, we'll be adding some additional step, right? So that step is actually not so complex, although it consumes some what do you call computation, some algorithm, but it's not so complex in terms of if you're going to do it really, like let's say we are making trees, when you're making trees, we'll be adding them. But if we don't keep on adding and deleting, but we do more searching, this becomes better. There are a lot of examples and practically shown that this algorithm works really well uh, for situations where the searching is more prominent than adding or deleting. Obviously, we have to add and delete so that we can make the tree. But when we do more search, lot more search to compensate for it. Uh, Someone says can't hear. Is it true? Hello. Can. Okay. Thank you. Maybe it was earlier. It was muted. Right. Okay. So let's now we had to actually look at the algorithm itself and the steps to follow. Uh, I actually explained these things, so I'll keep them for you to read. The cost of balancing, the advantage and the disadvantage. I mentioned it now, but you will also understand it better when we do it, right? So there is this idea of rotation. That is what we are going to do the balancing, right? So a tree can become not balanced. We saw examples. So here, these two trees are not balanced. The balance factor is beyond the number that is allowed, right? So you can see the how come this would have become unbalanced is by when somebody at this number or at this number, it becomes not balanced anymore, right? So that's the possible number to add. So this might be an order like the numbers were 20, 30, 10. 10, 30, fine, it's a balanced tree, AVL tree. When you add 20, it's still an AVL tree, like 30, 20. That will still be an AVL tree. But when 10 is added, it's no longer. So, by the way, why this is an AVL tree is the balance factor of this is 0, balance factor of this is 1, right? So now when you add 10, the balance factor of this is 0, balance factor of this is 1, the balance factor of this is 2, and it becomes unbalanced tree, right? So then we have to do something about the situation when we add 10 here. Same for 30. So the balance factor of this is when I had only 10. So the how this would have happened is 10, 20, 30, right? So these three numbers in a binary tree, we are adding 10, this a balanced tree because the balance factor of this is 0. When I add 20, this is still a balanced tree because the balance factor of this is minus. So balance factor of this node is 0. This node is minus 1. Right? So I add one more, 30. Now the balance factor of this is 0, balance factor of this is minus 1, the balance factor of this is minus 2. Now this node is unbalanced and therefore this tree is unbalanced. So the unbalance happened when I add, when I added the last element, it would have become unbalanced, and then we had to figure out what to do. So what we'll do is what is known as rotation, right? So I'm going to show you how the rotation works and how to do it. So basically rotation is the idea is to restructure the subtrees, right? So when there is an unbalanced node, we'll be restructuring the subtree such that the node becomes balanced. It's a simple idea. I'll show you examples to make it more clear, right? So while we are doing this restructuring, something that we should not forget is that we are working with a binary search tree, and therefore the binary search tree behavior. One is it is binary, second one is it searchable, meaning like it has left subtree smaller, large subtree larger. So we have to keep those properties maintained while we are doing the balancing, right? And what we have seen is this balance sub search, yes, I mean the balancing or the rotation is computationally not so complex. If you do, it basically consume one operation. But if you do it like every time, and if you keep on doing several times, it's going to add up, as you might know. Like if you keep on adding, keep on adding numbers, keep on deleting numbers on a tree, then several one together is so many nodes and so much complexity. But if it is only a few times and we do more search, then we balance out, right? And a balance, sorry, a balance, binary, sorry, a binary search tree, as also you might remember, maintain this in-order traversal sequence. So in a binary search tree, if you do an in-order search or in-order traversal, you get an ordered list, right? We have seen it in the last class, ordered list, right? So in-order traversal will give you in a binary search tree, and in-order traversal will give you a sorted list, right? So that has to be maintained as well. So it's automatic. Like if you maintain a BST, the in-order search and the in-order traversal property will automatically be maintained, right? So let's see how we do it, right? So I mentioned this at the very beginning of the introduction. There are four ways in which the rotations can happen. Basically, there are four ways that could cause the imbalance, and for each way there is a particular rotation that we have to do. One way, the very first one is the imbalance happen because of left subtree of a left child causes the imbalance, right? So we have something like this. Let's say a tree like this, which is a balanced tree, right? This is a balanced tree. Why it's a balanced tree, I already explained a little while ago when I was talking to you about this 30, 20, 10 example, right? So that's a balanced tree. Now, the imbalance could happen when I'm adding a new node to this actually. So if I'm adding a new node to it, let me change the color, and I add a new node to it here, then that's imbalanced, right? So this is imbalance where not in this node. This node it's balanced because the balance factor is 0. This node it's balanced because the balance factor is 1. This node it is imbalance. Maybe I should have used the opposite notations. Oops. So this is balanced. This is balanced. This is not, because this is balance factor 0, balance factor 1, balance factor 2. So now this is imbalanced. Why? This node is imbalanced because of a left node or a left child or a left subtree, right? So this for 2, node 2, that is the left subtree, right? And why in the left subtree the imbalance has happened is because of the left child, right? Because of this is left child. So that is exactly case 1, right? The imbalance here has happened because of the left subtree and also the left node of the left subtree, right? So if you take this subtree, this is the root and this is the left node, right? Or the left child. So this is one way of imbalance. The right mirror of this is the right? So you can have one like this. And when I'm adding something here, this can go imbalance. And why it has gone imbalance is because of this node is imbalanced now because of the right subtree and also the right side of the right subtree, right child of the right subtree. That's this case, right? The first case is this. The right mirror of this is the other case. There could be two other cases, right? One other case could be, let me use another color without deleting anything else, green. So one other case here in the first left side is that, let's say this is not there. Maybe I should delete so it becomes easy. So the imbalance would have happened even if it is this. Oops. Imbalance would have happened even if it is this. Right, because this node is 0, this node the balance factor is, I mean, the height of this one is 1, and therefore the balance factor of this is still 2, right? So same applies on this as well, right? So on the other one as well, meaning even if I don't have that, green color, even if I have this, still this is this row, this node is not balanced, this node is not balanced. But these two are like mirror, but in a different way, right? What I mean is this imbalance has happened because of the left subtree, but the right node of the left subtree. But it's the left right option. So the left subtree, but right node. The right left option is just the opposite. The right subtree, but the left node. Right subtree, left node. Sorry, maybe I'm just confused with the two. I'm writing the opposite one. So this is the left, left, right, right subtree, left node, and here the left subtree, right node. It looks like I have written the other way around, but the idea I hope is clear. I'll just double check and update that the way how I written it. But the idea is that this can happen in 4 different ways to mirror image of the other two. One, it could be just the left subtree of the left node, left subtree of the right node, right subtree of the right node, right subtree of the left node. So those are the 4 different situations an imbalance can happen. The imbalance has happened always in this node, right? Only on this node the imbalance has happened, and it has happened because of either the left subtree or the right subtree, 2 cases. And if you take within the left subtree or the right subtree, it would have happened because of the left node of the left subtree or the right node of the left subtree, or the right node of the right subtree or the left side node of the right subtree. So those are the different options that are possible, right? So there are basically 4 different options. So these 4 options, there are ways, standard ways, fixed ways of fixing them, right? If the problem is left, if the problem is on the same side, something like this is what I mean by same side. Here also same side like this. So the same side problems are both the letters are same, left, or right. Other problems are opposite side problem like this or like this, opposite side problem. These are same side problem. These are opposite side problem. In both problems, I hope you realize the height is still the same. I mean, the height is bad, right? So height can be bad. The example I was giving you is always like this. But it doesn't have to be like that. A height can be bad by having a zigzag. This also height bad. There's no difference. It could be just one squid or it could be just zigzag, but still the height is bad, right? So I hope you understand that idea, although I didn't show that earlier as an example, right? So these are the 4 different combinations where things can go wrong. For each one of them, there is a standard method to follow. So I'm going to show you those methods as examples. So before example, I also have like some notation based one, right? So if I have like this, what do? Is I do what is known as a single rotation. So I do what is known as a single rotation that is mentioned here. What I do here is what is known as a single right rotation. Oops. A single right rotation. Right rotation means like I'm going to rotate like that. Left rotation mean I'll be rotating like this. What do I mean by rotating? Let me show you how it works. So this rotation will make, let me go to the next slide. I think I have that example here. Yeah, so the same thing I had is Z, Y, X. Now I rotated. By rotating, I'm bringing Y up, Z here, X here. That's what this is. right? So when I do that rotation, if you carefully look at it, I'm doing a lot of changes actually. A lot of changes to the links. Like these arrows, I mean, the lines are basically the child, right? So they are pointers. So one thing I'm doing is I'm changing Y to be the root, right? The subtree's root that caused the problem becomes the root, right? So now this is the root, and the original root is going to be the left subtree or the left side. I'm calling it the left subtree because in this example, there's nothing on here. But if I had something there, that would still be here, right? Right now, there's nothing. And the rest remain the same, right? So one, I am making this no longer the root, but the subtree of y, and therefore y become the root, right? So that's the rotation I'm doing here. I hope that is clear. If you have any questions, please clarify. And the same applies for the opposite rotation as well. Like if I have the other side, I'll be doing rotation this way, the left rotation. So left rotation will make y the root, and is that here, x here, right? So that's the opposite side of the rotation, which is called the left rotation, right? So because it's left side, and the other one we did is the right. So if we have an RR case, right side subtree, right node is the cause for the imbalance, we'll do a left rotation. If you have an LL case, a left subtree, the left node is the cause, we'll do an opposite, the right rotation. The right and the left rotations is what we are going to do there. So those are the first two cases. So the next, so this is the balanced one after doing the rotation. Next one is a little more the zigzag case, right? The zigzag case, actually we'll do a double rotation. As I have mentioned here in here, right? So I'll do a double rotation. A single rotation won't work here. We'll have to do a double rotation, right? When you have zigzag. So basically the LR case, so left subtree, right node. I think earlier I mixed it up. Sorry about that. I'll fix that. So this is the cause of this imbalance is the left subtree, but in the left subtree, it's the right node that is causing it. So that's the case is left subtree, right node. Right? That's how it causes the issue. So how the opposite of that is also true, right? So the RL case will be the right subtree, but the left node, right? So it's inside. This is the other zigzag, the mirror image of that zigzag, right? So both of these zigzag, we'll have to do two rotations. So we call the double rotation. I'll show you how the double rotation works. It's not so difficult. Actually, the double rotation is done to make, we'll do two steps, two rotations. The first rotation is done to make a complex case like LR or RL to become an easier case like RR or LL, right? So I'll show you how. I see some message. Might have. Oh. No, so when you have more heights, there's a question what happens if the height is higher, more, right? So when you have more heights, the imbalance will happen somewhere lower, right? So you'll have to fix the imbalance in the right place. Right? If the height on one side is higher, then the imbalance would happen like so. By the way, so although I am showing this example as it all happening in a tree and this is the root, that's not true, right? I explained that earlier as well. So this part could be part of a bigger tree. No, three lines, only two. I do that one. Right? So this could be a big tree and Z can be there. If there's an imbalance here, the reason for that imbalance is this, and we are fixing it here. So every situation, it will be like that. The imbalance will be happening at a place where one side is two more than the other side, right? So we have to find the lowest place where it's happening and fix it, right? So I hope I answered that question, and therefore the question you asked won't appear. Actually, it appears like for a place like this, it is true, it will be more, but we will not let the imbalance factor go beyond 2. You might wonder, okay, can the imbalance factor be 10? No, it won't be 10 in an AVL tree because we would have been already balanced it. So it can go beyond 2 or minus. So it can be like beyond 1, which is 2, or beyond -1, -2. When it goes to -2, we'll fix it. So then it will become -1. So next insertion, it will again can go to -2. It can't be -3, 4, 5, 6, and all that. It will never happen because we will not let it to go that level. So if we let it go, then we can't fix it. This algorithm won't work. So the imbalance will be fixed as soon as it happens. So a single insertion can make only the imbalance factor just by one more. It will be immediately fixed. I hope I answered that question. And going back to this discussion, the something like this, how do I fix is I do 2 rotations like I told you. What are those 2 rotations? First one is this, right? So remember, this is what I had. Y, we had Z, Y, X. So we originally had Z, Y, X here, a zigzag, sorry, X here, right? That is what we had. And the imbalance has happened because of the left-right issue. What do I mean by, so imbalance has happened here? It's a left-right issue because it's on the left subtree and the right node, right? So that therefore it's a left-right issue. So there's a question when implementing the code, we have to check the balance in every node, creating iteration. Yeah, that's correct. We'll be checking and we'll be stopping and doing the iteration at the lowest level, right? So we'll be checking. Yes, that's correct. We'll be checking it's a recursive process because so in fact, like the recursion happens. So when you do an insertion, the next thing you'll do is we'll look at you'll go from that insertion upwards and find the imbalance node and we'll fix it. So it happens in a recursion. Yeah, so going back to what I was explaining, so here is what it was, and what I have done here, as you can see, first step is I have made a tree like this. But in this tree is I have done a rotation not at this node, but in the subtree. I have rotated this subtree, right? So is that, and X becomes here, and because I rotated, I made X here, Y is going to come down. So that's going to be Y. That is what you are seeing here. So I done a single rotation, a left rotation, right? A left subtree right node problem. We'll do a left rotation first on the subtree. So we get this tree. When you have this tree, we already know the solution to this tree because this tree is the left issue. This is the left thing we saw earlier. The cause of the imbalance is because of the left subtree and the left node. And you know how to fix it. Left issue, we'll fix it by doing a right rotation. So we have done a right rotation on this. So it's not right. Okay, looks like I lost battery. Yeah, so we'll do sorry, I didn't keep my pen charged. Okay, let it charge. So the first thing is the left rotation. First thing is the left rotation of the subtree, And the second one is what we have already been doing, right? So when the tree now is left issue, we'll do a right rotation. It get fixed. Yeah. How do we know? So there's a question, how do we know X is smaller than Z? X is smaller than, okay, how do we know X is smaller than Z? You can get the answer to that from here, right? So X is smaller than Z. So anything here is, anything that is on the left side of Z is smaller than Z, right? So we don't really have to worry. Like, by the way, we don't have to really, yes, I told you earlier, we have to maintain the BST, binary search tree property. But if you follow this procedure, it is automatically taken care of. The maintaining of the BST is automatically taken care of. You don't really have to worry about whether we are violating it, because it's not going to be violated, right? So X here is, the question asked is whether, how do we know X is smaller than Z? We know X is smaller than Z because X is on the left subtree, right? So we are only dealing with the left subtree, and therefore everything on the left subtree is going to be smaller than Z. In the key principle, X is the bottom value. I'm not clear of that question or a comment. If it's a question, please ask again about the last point, key principle. Anyway, so the point is, yeah, X, anything on the left subtree is going to be smaller than Z, and therefore it's possible to make any rotation here to, and it, any node here in the left side can be the root and can be this left sub, can be part of the left subtree of Z, because there's no, nothing has changed. And also, obviously, if you are bringing Y as the root, Z can go to the left side, sorry, the right side. That also is obvious. So in terms of, so yeah, I hope you saw why X is still a valid answer, because X is larger than Y, and X is larger than Y. How do I know? You can see from here, X is larger than Y, right? So X being here is the perfect position, and X and Z being here is again the perfect positions. So because the order is, the smallest element is, you can see from here, the smallest element here is Y, right? Because X is on the left right side of Y, which is why X is larger. Smallest element is Y, next is X, and the next largest is Z. That's the order, and that the order is still maintained. Right, so the I will not explain the opposite of this because it's just a mirror image, right? So if I have it on the other side, I'll do the two rotations just the opposite way, right? I'll do the right rotation to make make it like an RR, right? So which is here. I'll do a right rotation to make it like this is an RR problem, right subtree, right node. So RR problem. If it's an RR problem, I'll do a left rotation. That's what I had done second. So in cases where we have the RL or LR issue, where the left subtree or the right node of the left subtree or the left node of the right subtree is causing the imbalance, then I'll do two steps. The first step is to make it into a problem like the first type of problem, which is RR or LL. Right side, right node of the right subtree, left node of the left subtree. Then I'll do the second step, which is just the same as the previous one, right? So those are the four steps. Here is a summary of rotations. So the four cases, and two cases are zigzag, two cases are straight lines. And in all four, first two cases, straight line cases, we do single rotation. Zigzag cases, we'll do two rotations. Right, so that's basically what we'll be doing. I have some example here. I think examples are like for you to get some solid in your head, but the idea is exactly what I have explained here. Right. By the way, the examples, because of its slides, I have written them like this. Right. So that is if you are inserting 30, 20, 10, which is an example we already had, and how the balancing will work. is what is written here, right? So let's say we are inserting, let's see whether, right? So we are having 30, 20, 10. So 30 is the first node, balanced. 20 is the second node, still balanced. Why it's balanced? Because the balance factor of this is 0, the balance factor of this is 1, still balanced. We are putting next one, 10, not balanced anymore, because the balance factor of this is 0, balance factor of this is 1, the balance factor of this is 2. We already discussed this, the same example. When it happens, then what you have to do is we have to do, this is a situation with LL, left subtree, left node, then we have to do a right rotation. What is the right rotation means? We'll make this the root and make 30 here and 10 here. So that tree is the balanced tree. It's a simple example. You can look at more complex examples as we go. I mean, as you can try out more complex example. I have also given some examples for you to try. In fact, like the complex, there is no complexity if you ignore all the other complexities that are in the tree. So we have to just focus on the node that has the problem and fix by moving the subtrees around. Right. So that's exactly what you have to do. So here it's one rotation. So this is like a different one, the zigzag problem, right? So if you have a zigzag problem, then you'll be fixing it by doing two rotations. So 30, 10, 20 is a zigzag problem because it will be like this. So 30, then we put 10. So therefore it, 10 is on this side. And then 20 is in between the two. So it's going to be here. Right. So a situation like that, we'll do because it's like this, we'll have to do one rotation first like this, and then a rotation like that. So first rotation will make it to 30, 20, 10. So when it is 30, 20, 10, we know it's a previous problem. So can rotate the next one to make it 20, 30, 10. Right. So that's what we'll be doing. Right. So it's the two rotations. So here is the order in which the algorithm works. I haven't gone into detail. Some of you are asking this question already. So insertion works like the binary search tree insertion. We already have discussed this: traverse, find the place, and insert. And we'll be updating the heights based on the insertion, because insertion will change the heights. When the heights are recalculated, we'll also calculate the balance factor. Balance factor is basically the height between the two sides. So we'll be maintaining the heights inside the node, and then we'll be updating the heights, and then we'll do a balance factor. And the balance factor, if it is above 1 or minus, so basically -2 or +2, then we'll do the rotation. Rotation, actually I'm calling it rotation, but if you carefully look at it, it's just updating pointers. Rotation is updating pointers, right? So the updating pointers has to happen, like which one is the child, which one is the parent, those things are changing, right? So that change we have to do, right? So we had to be, so this is I'm calling it the hotspot. So we'll have to clearly identify, this is the focus point, right? If you have a bigger tree, and when you do an insertion, we have to clearly identify where the imbalance has exactly happened. And I also have mentioned here, right? So in an imbalance situation, when there is a single insertion or deletion happen, there will be at most one rotation. Only one rotation will happen. One rotation, when I say one rotation, it could be one of the four, right? One of the four cases, LL, RR, LR, RL. One of the four cases. It could be one rotation like a single or a double, but there'll be only one for a single insertion or deletion. So the self-balancing has to finish that before it goes to the next step. So little on the complexity, I already have mentioned this, right? So the AVL tree guarantee 1.44 height coefficient. So it's basically log 2n 1.44. So in terms of big O notation, it's just log n, log base to n yet. But compared to a regular BS tree, a binary search tree, the worst case could be n, the total number. So it's really bad. The 1 million versus 20, or now it's 30, or even less than 30, right? So that's sort of a, when you have larger number, that's what it is. So operational complexity also listed, worst case. In binary search tree, searching, insertion, deletion, if it is like a skewed, or it could be like the zigzag skewed, all of them could be worst case, that then the number of comparisons worst case is n. But here AVL tree, it guarantees 1.44 log n. In big O notation, it's basically log n. Rotation cost, every rotation cost 1 in big O notation. So if you have several of them, then it's not a good idea, right? Um, So AVL tree, I think you can just read and understand this. I'll not explain because I already have been talking about the same issues all this time. But then there are some limitation. The implementation complexity, it become more complex. If you do more rotations, if we are doing lot of rotations, meaning if you are doing updates, more updates than search, then this is not a good idea, right? And we also have additional storage as well, right? So there are problems with the storage when we do this additional because we are going to add the height to it. So there are other alternatives like red black tree and other type of trees which are used in certain places, uh, and we will discuss about them later. And so this, I think I just have included few other things for you to read and like remember. I have mentioned these things already. One point I already have mentioned this as well, but I have put it here is when there's an application where there are a lot of search, then this is best. But if there are application where there are a lot of updates, changes, then this is not a good idea, as you can see, because then we are going to be doing more rotations than searching, right? So if you do like update, keep it, and do a lot of search, so applications of that nature, this is good and it has a predictable performance. So the performance is going to be, the search performance is really good, like 1.44 times. So big O notation log n. So this is not good for load. If you are doing a lot of writing, it's not good. Um, it's not also good for certain other memory related issues, like if you want to keep maintaining more memory, that's not also a good idea. I mean, sorry, this will consume more memory. So it's not a good idea if we are using a memory constraint situation. We have to figure out other options. So we'll discuss those as we go. So some limitations. So this I will not repeat. I just have been talking about it. It's included a summary. And I also have some exercises. So by the way, next class we'll be talking about red black trees, and you'll also have practical classes on this. I also have included a couple of exercises for you to try, a few exercises. Uh, I'm not going to discuss them here, but I have already uploaded the slides, so you can look at those exercises and try them out. Yeah, that's all what I have. If you have any questions, you can ask. Yeah, there's one comment that these lectures are more effective than the physical classes. Let me ask others. So you have other class as well, something else, I think at 12 o'clock, because your lunch break is, yeah, I realized that later. Yesterday I mentioned, made a comment. Yeah. So you can go ahead with the next class. We'll think about this. Yeah. If you think this is more effective, we'll consider this option. Yeah. You can go to the next class. Thank you very much. I'll put a poll to ask some feedback from you. Yeah. Okay. Thank you. Okay. Today no lecture. I see.